yesterday we saw that we can split some groups into subgroups and write them as a product of two groups. And we saw one example which was Q star, which we split as specifically two subgroups, where the first one was just powers of 2 and the second one was all the rational numbers where numerator and denominator are odd numbers. Now, one thing that I would like you to observe, which is also an interesting phenomenon, is that if you consider the subgroup H1 here, it is all the powers of 2, positive and negative. This is in itself a group under multiplication. Does this group look familiar to you? And when I say familiar, of course, it's powers of 2 to it. These are very familiar numbers, but is it a group that you have already encountered before in this course? It's sort of addition. You think so? Why? That's right. I mean, it's in the exponent. If you see, of course, there is a 2 at the base, but in the exponent, we are just have all integers, positive and negative. And the multiplication, the group operation, which is multiplication, is the addition operation of numbers in the exponent. So, at least if you think of this group as operations happening in the exponent, it is simply the group of integers under addition. But that's seeming so, but it's not precisely so. We need to have a more precise correspondence between these two groups if we really want to claim something about them. And thankfully, the notion of isomorphism is just the one that we need. Group which consists of powers of 2 under multiplication is isomorphic to the group of integers under addition. I should say Z plus. Well, for the proof, I just need to exhibit a mapping from H1 to Z, or conversely from Z to H1, which is 1 to 1 on 2. And preserves the group operation. And that's simple. At least Z to H1 is easier to describe. Phi of n equals 2 to the n. This is a 1 to 1 on 2 map from Z to H1. Does it preserve the group operation? If you, in the domain, if you add two numbers, say n1 and n2, so you consider phi of n1 plus n2, is by definition 2 to the n1 plus n2, and that is 2 to the n1 times 2 to the n2. This is phi of n1 times, and this is phi of n2. So, it preserves the group operation. It is a 1 to 1 on 2 map, and that's precisely the definition of an isomorphism of groups. So, when two groups are isomorphic, we really have the same group really. The only difference is the way the symbols we use to write that group is different. So, the moment we realize that H1 is isomorphic to Z, we can go back to where the H1 came from, and we can write Q star as isomorphic to Z cross H2, where H2 consists of rationals with odd numerator and denominator. So, that is already a very interesting fact, that although we had both are sets of integers we started from, both the groups Q, not integers, sorry, Q star and Z, they are related groups, but we found a whole copy of Z into Q star. In fact, we can find more copies of Z in Q star. If you look at H2 and take out all powers of 3 from H2, so if you define H3 as all rational numbers where numerator and denominator are neither divisible by 2 or by 3. So, this is taking out an all powers of 3. So, I can take out that there is another group which we have taken out, which is all powers of 3. That is also isomorphic to Z, for the same reason that all powers of 2 are isomorphic to Z. Then we can write Q star as isomorphic to Z cross Z cross H3. And now we can continue this exercise. H3 we can replace by Z cross H5, all powers of 5, all primes. We can just continue with this. So, that is an interesting fact, that you can write Q star as copies of Z multiplied with each other. The next question is how about Z itself? Can we write Z can we further divide Z into two groups, a product of two groups rather? And the answer to that is no. And I should say, just to be very correct, there are no non-trivial groups. I can always define G1 to be Z and G2 to be just the identity element, and then obviously it is a product, but that is really not saying anything interesting. So, no non-trivial groups. A non-trivial group is a group which is something more than identity. And this is also quite a remarkable theorem that says that we can't write Z as a product of two subgroups. The proof is very easy actually, and that proof itself will lead us to something interesting. Let us prove it by contradiction. Suppose there is an isomorphism. Consider where does the number 1 go. number 1 will be mapped by this mapping phi to some element of G1 cross G2. So, let us say this is H1 comma H2. Then where does 2 go to? 2H, 2 is 1 plus 1, yes, that is right. And because phi is an isomorphism, this is same as phi of 1 plus phi of 1, we are writing this group, these two groups also additively here, and that means it is 2H1, 2H2. Here I am taking some liberty with the notation, 2H1 is H1 plus H1. And in general, phi of k would be k H1 comma k H2. And this describes the entire range of phi, because in the domain, I mean, if you look at Z, there is just all possible values of k, positive and negative integer, and that is mapped to these elements. Now, phi is an isomorphism. So, phi, the range of phi is entire G1 cross G2. So, that means in this range k H1 comma a k H2, these elements cover the entire G1 cross G2. Is that true? Is it possible? See, phi 1 is H1 comma H2, phi 2 is 2 H1 comma 2 H2. Now, in the fact that H1 H2 are in G1 G2 means that, well, 2 H1 and 2 H2 are also obviously there. Then since H2 is in G2, 2 H1 comma H2 belongs to 2 H1 comma H2 is in G1 cross G2. So, it must occur in the range of phi. So, 2 H1 comma H2 is k H1 comma k H2, and then this is the two group elements, you take this, subtract them, you get k minus 2 H1 comma k minus 1 H2 is 0. Is that possible? That will make both G1 and G2 finite elements, unless k itself was, well, so the first thing is k can be either 1 or 2, it cannot be simultaneously both. So, it can only make one of the two components 0, and then it would mean that others. So, assume without loss of generality, assume k is not equal to 1, then k minus 1 H2 is 0. This implies that the element H2 is very special. You add H2 to itself a few times, you get 0. So, now let us see. What is the simplest way of showing that we will get a contradiction? If you look at phi of k minus 1, that is going to be k minus 1 h1 comma 0. Okay, and how does this help us? Any suggestions? Not necessarily. Not they have.
If we add, see the G1 consists of only H1
Multiples of
and
H1.
so on, yeah.
G1 considers only multiples of H1.
And
G2 considers consists of only multiples of H2.
And after
And
a point,
okay, and after a point H2 multiples become 0. So that's right. So G2 is finite group.
even G,
But is that a contradiction?
if both of them are finite,
If both of them are there, it's a contradiction. But G1, G2 is finite and G1 is infinite. Then one-to-one relationship is violated.
Because integers are
Why is it? Why?
So you are saying that G1 is infinite and G2 is finite.
G1 is infinite, G2 is finite. Yes.
So we can think H1 and 2H2.
H1 into
We have taken example 2H1 and H2.
2H1 comma H2.
So we can take H1 and 2H2.
No, we cannot multiply them. These are G1, G2 are two groups when we are just looking at the product of the groups.
So yeah.
what is he saying is H1 and 2H2 are also a member of G1.
H1 and 2H2 are members of the range.
So we will proceed, then we will get to G1.
Let's not spend more time on this. Work it out. This is a simple assignment problem. Okay, I am just losing my way somewhere here. It's a very simple proof. Okay, so that tells us basically that Z cannot be divided further into two smaller subgroups. So in some sense, Z is a indivisible group, Z under addition, and Q star is not. So why is that happening? Why is it that Z is indivisible? The way this proof goes, that should give you a hint. We looked at where does 1 go to, because 1, once we know where 1 goes to, all other elements of Z can be decided. So that leads me to the definition. So we say an element small g of a group capital G is a generator of the group if the entire group can be written as in terms of small g. So here I am writing group G as multiplicatively. So I am writing taking powers of small g and writing G as set of all powers. And that's the example that we had already seen. 1 in Z is a generator. Does Q star have a generator? one number whose different powers generate the entire Q stars? No. On the other hand, 2 to the n, of course, has a generator, which is 2. So, the existence of generator is the difference, which is making Z indivisible, whereas Q star is not. And this observation can now be extended further to a more general definition. So, group G is called a finitely generated group. If there exist finitely many elements in G, G1, G2 to Gk, such that every other element of the group can be written in terms of these elements G1 to Gk, and this is the general form of the various element written in terms of G1 to Gk. Here alpha 1, alpha 2 to alpha k are integers. So, what are finitely generated groups? Well, of course, Z plus is finitely generated. It has only one generator. Is Q star finitely generated? Actually, the number of generators are in Q star is exactly equal to number of primes, and that is infinite. So, Q star is not finitely generated. The restriction of Q star, where we can say, let us say, all A by B, where A, B are consider all primes numbers up to some upper bound R, and then look at all rational numbers A by B, where A and B only consist of primes up to R. This is finitely generated, because now you only have finitely many prime numbers with which all the numbers are written, and that is finitely generated. Any other example of finitely generated groups you can think of? It's not easy to find out an example of a finitely generated group. There are many, but most likely you have not come across them. So, let me give you an example, another example, without giving any more details of this example. Maybe later on, if we have time, we will come back to this example, which is look at this cubic curve y square equals x cube plus ax plus b with 4a cube plus 27b square not equal to 0. These are very technical conditions. And look at all rational points which lie on this curve. When I say a rational point, the obvious meaning is that the coordinates of those points must be rational numbers, both coordinates. And one can show that there exist infinitely many such points. They form a group under a certain addition operation, and that group is finitely generated. But to show this is a very non-trivial exercise, and it took very long time for mathematicians to prove it. So, recall that we started with the aim of understanding the structure of groups, and all this exercise we have done so far, expressing it as a product of smaller groups, etc., is geared towards it. Now, I am going to give you a big structure theorem, which is very general. It applies to all finitely generated groups, and it completely describes the structure of these groups. Let G be any finitely generated group. And in this course, I have already said yesterday, we will discuss commutative groups. So, whenever I say a group, I mean commutative groups. This theorem does not hold for non-commutative groups, so it is only for commutative groups we are talking. So, if I talk about non-commutative groups, I will say I am talking about non-commutative groups. Otherwise, when I say group, it is a commutative group. So, G is a finitely generated group. Then there exist two numbers, integers, n and m, such that G is isomorphic to z cross up to z, m copies of this, cross G naught, where G naught is a very small group. It is a group, actually it is only a finitely many elements, which actually n elements. This is describing the structure of any finitely generated group, and it is a complete description, because Z we have already seen you can't further split it, and the structure of Z is very simple. There is just one element 1 that generates this entire group in a very simple way. So, really we can't have a simpler group than Z, and there are m copies of Z present in it. And then there is a tiny bit of extra, a finite group, which sticks out. We will not prove this theorem, I just give it to you to show that this exercise of abstraction and going through all this analysis does have some very interesting consequences, that we can prove a structure theorem like this, and which is applicable to a wide variety of groups coming out of various domains. And once we have proved this theorem, we do not have to prove it specifically for the groups we encounter, we already have it. Now, let us continue further our investigation into groups. This is a nice theorem to know, but this is still not a complete picture of groups, because just look at Z. I have said that you can't split it further, but still Z does have subgroups. All even numbers we saw yesterday is a subgroup of Z. And I cannot write, unfortunately, Z as a product of even numbers times some other subgroup, because there is a, it's not feasible. But we would still like to understand the various subgroups of Z and how they relate to each other. And for that, we will use the notion of homomorphism that I have already defined just before defining isomorphism. A homomorphism is a mapping between two groups such that the group operation is preserved. There is no requirement of the map being 1, 1 and not 2. So, consider the following map. It's a simple map, multiplication by 2. When I write 2Z to represent the subgroup of Z, which consists of even numbers. So, phi is a homomorphism. It's trivial to see, yes. The addition of two numbers is mapped to 2 times the addition of those two numbers, which is just 2 times one number plus 2 times the other numbers. The range of phi is all even numbers. Right? And that's a subgroup of what does it leave out? Phi. Phi leaves out all odd numbers. In fact, if you see Z and divided this into even and odd, even numbers and odd numbers. So, this is range of phi. This is not outside the range of phi. However, I can write this as 1 plus range of phi. And this kind of leads to the following viewpoint, that let's call 2Z to be range of phi and define the following relationship. We'll defining a binary relation on Z, the set of all integers, and the relation says n is related to m if and only if n minus m is an even number. Do you remember equivalence relations? This relation R is an equivalence relation for obvious reasons. A number n is related to itself because n minus n, which is 0, is an even number. Then reflexive property, n is related to m, which also means m is related to n. And transitive property, n1 is related to n2, n2 is related to n3. That means n1 minus n2 is even, n2 minus n3 is even. That clearly means n1 minus n3 is even. So the relationship is transitive. So R is an equivalence relation. This equivalence relation, as we know, any equivalence relation divides a collection of elements into equivalence classes. So for this particular relation, we will divide set Z into equivalence classes. What are the equivalence classes? Odd numbers and even numbers. These are just the two equivalence classes, and those are precisely these. This is one equivalence class, this is the other equivalence class. Now this leads to a more general observation. This we saw in terms of Z and a particular subgroup of Z. But now let us consider a general group and a subgroup of Z. And we do the same thing, just mimic that exercise, define an equivalence relation. Or first define a relation, we will show that it is an equivalence relation. So A is related to element B. Now we have to define it with respect to the subgroup H. And just remember what we did. We did the subtraction of the two elements. That should be in the subgroup. Let us write this group multiplicatively, as we would typically do for a general group. So there we have to say A B inverse is in H. A minus B becomes A B. B inverse represents the inverse element corresponding to B. Now it is straightforward to see that this R is also an equivalence relation. For exactly the same reasons. A is related to A. Okay, maybe this requires a proof. A related to A since A inverse, which is the identity. Let us write the identity as E, and this belongs to the subgroup H. Since H is a subgroup, it has the identity. A related to B implies B related to A, since A related to B means A B inverse is in H. H is a subgroup. So inverse of this element, A B inverse, is also in H. What is the inverse of this element? B inverse. And A related to B and B related to C implies A related to C, since A B inverse in H, B C inverse in H implies that product, again because H is a subgroup, the product is also in the subgroup A C inverse in H. So it is quite remarkable that the notion of equivalence relations seems to fit perfectly with the notion of groups. You see, the identity of group is corresponding to the reflexive property. The inverse property corresponds to the symmetry, and the closure property corresponds to the transitivity. So, the net result is that the group G is now divided into equivalence classes, and these are determined by the subgroup H. You have GG, then you have H as one equivalence class, the group subgroup itself will be in one equivalence class. Then there will be other equivalence classes A1H, A2H, and I will explain what I am meaning. Actually, it's A1H is simply all elements of the form A1 times an element of subgroup H. Why are these any two elements related? If you look at A1 H1 and A2 A1 H2, these are two different elements in this. They must be related to be in the same equivalence class. The relationship property says A1 inverse H1 H2 inverse. Why are elements in A1H in the same equivalence class? That is a question. So, take two elements in A1H, call them A1 H1 and A1 H2. Their inverse, so let me just write this again. What is their inverse? A1 H1, A1 H2 inverse. This should be in H. So, this is A1 H1 H2 inverse A1 inverse. This is a commutative group. So, A1 inverse takes care of itself. This becomes H1 H2 inverse, which is of course in H. So, the commutativity here is essential. If you do not have commutativity, there is a problem. And this is how we can show that any two. So, clearly all elements in here are in the same equivalence class. How about two elements across, can they be in the same equivalence class? That is, so there is one property. Then let us look at one element from A1H and one element from A3H. Are they in the same equivalence class? A1H1, A3H2 inverse. This is A1, A3 inverse, H1, H2 inverse, just rearranging the terms. This is of course in H. So, this is A1, A3 inverse. That element will determine the equivalence class it is in. So, let us say assume without that it is in A1H. Okay. I am saying that all of these, each one of this is contained in equivalence class. The question is, can two of them all be contained in one single equivalence class? So, this is one element from here and one element from here, and suppose this is contained in the same equivalence class, which is that this is in H, of course, here this is in H, this should be in H, right? That is when it is in the same equivalence class. H1 H2 inverse is in H. So, this would imply that A1 A3 inverse is in H. Okay. This implies that A1 is in A3H. So, these two classes are equal. If A1 is in A3H, then A1H is in A3H. So, that is the other part of derivation. So, at the end we have group G is split into disjoint equivalence classes, each equivalence class being of the form some A1 times H. Okay. Now, I will do a little bit of magic. Let us collect all the equivalence classes, okay, and put them in one set, call it G hat, and let us define an operation on G hat. The dot operation on G hat is defined as AIH is one element of G hat, AJH is another element of G hat, they are operated on each other. You get AKH, which is the third element of G hat. This is AK is that element of G such that AIAJ belongs to AKH. And we state the theorem which I will prove later. Under this operation, this set of equivalence classes itself is a group. This takes some time to absorb because elements of G hat are not elements of G, they are sets of elements of G. And we are operating on sets of elements through this dot operation to creating the different sets. And these operations themselves produce a group structure on G hat. We will continue.